That is two possibilities of deactivation. Next, third one. Coupling with ground state partner. Third possibility. So what is our final intention? I want to deactivate excited molecule. Two ways. Deactivation by releasing heat energy. Deactivation by releasing light energy. Now products. Up to now we not discussed any product. So this is excited molecule. See, initially ground state. Now photochemically excited. Okay, this is S1 state. Now it is combining with a ground state partner. See, it is excited. What is this? Ground state. Excited partner combined with ground state partner. Then what happens? See, you will get one reaction. This is called coupling reaction. This is oxygen coupled with this 2-methyl and here pH and this is pH. This is called Paterno-Bush reaction, PB reaction. How many molecules are combining? 2 molecules. Out of 2, how many are activated? Only one is activated. See, this is ground state. Don't write this. See, this is ground state. This is excited state. Who is ground state? Carmel is ground state. It is excited over here. Now Carmel is excited. Now it is excited molecule combined with a new ground state molecule and it will give a product. This is a product. No deactivation to ground state. Excited molecule combined with a ground state molecule and you are going to get this product. This product is this one. Is it a deactivation? Yes, it is also deactivation. Deactivation means losing excited energy. Don't think that deactivation means coming ground state. Coming ground state is one of the part of deactivation. Okay, excited molecule may give product. Excited molecule may come back to ground state. That all are deactivations. So this is called Paterno-Bush reaction. Excited molecule coupled with a ground state molecule is PB. Next. Fragmentation. Alpha, beta, gamma. This is ground state. Now photochemically excited. Here are double bond or like this. It is photochemical excited. Alpha, beta, here gamma. Now after excitation they undergo fragmentation. This is called Norris-2. Norris-2 reaction. McLafferty. See, is it ground state or not? Ground state. Ground state taking energy. Ground state taking energy in the form of light. And it is excited. See, star A written. Excited. S1 state. Once if they reaches to S1 state, then they want to lose their energy. They will undergo fragmentation. Means they will break into small pieces. So that is called fragmentation. Excited molecule coupled with ground state, excited molecule undergo fragmentation, that is Norris-2. So Norris-2 is an example of fragmentation reaction. So remove this hydrogen, break this and break this. It is a McLafferty rearrangement, Norris-2 reaction. You can say when pyrolytic sin elimination, reverse thermally. See everyone, is it unsaturation or not? First saturation, second saturation, third saturation. Yesterday we discussed. If third carbon having saturation, what is your answer? Retro-ene reaction. Thermally, if I use thermal symbol, below if I write any thermal symbol, what is that reaction? Below if I use thermal symbol, what is that reaction? Retro-ene reaction. Excited molecule undergo fragmentation. It is one more kind of stability. This is called PB reaction, Paterno-Bucci reaction. Paterno-Bucci reaction. Fifth one, isomerization. Excited molecule undergo isomerizes. Isomerization means this is activated S1 state responsible to give. So this is a trans isomer and this is cis isomer. Initially I taken cis isomer, photochemical activated, I got a transition state. Activated molecule will give trans isomer. Cis trans isomerism possible under photochemically. So this is last one, ejection of electron. It is S0 state, photochemically activated. Once photochemically activated, it is excited. Here two electrons are present. It is S1 state. Now excited molecule may lose one electron. If one electron is removed, then what happens? You will get deactivated. So excited molecule, if they lose electron, it is also one kind of deactivation. Molecule having two lone pairs. Photochemically two lone pairs are there. Excited. It is excited. After excitation, if this molecule loses one electron, it is found to be radical cation. So this is unstable. This is little bit stable as compared to this one. Clear? These are the 6 ways to deactivate any molecule. It may undergo couple, it may undergo fragmentation, or it may undergo isomerization, otherwise they may lose electron to attain stability. Ejection of electron will attain stability for excited molecule. From here to here deactivation. From here to here deactivation. Okay, so that is about importance of photochemical reaction, sources of photochemical reaction, and how to activate and how to deactivate. What is the use of activation? Once if it is activation, how to get a photochemical product? Suppose the photochemical product is not possible, how that excited molecule returns into ground state? Total 6 possibilities are there. Deactivation by releasing heat energy, deactivation by releasing light energy, excited molecule undergo coupling with ground state partner. Best example, Pattern-Buch reaction. Excited molecule undergo fragmentation, breaks into small pieces. Then excited molecule undergo isomerization. Cis-trans isomerization with one molecule possible under thermally or photochemically. Photochemical. Even the DL exam, that question is given. Cis-trans isomerism. Cis-trans means one molecule is cis. I want to convert that cis molecule to trans molecule, possible under photochemical. Okay. Then followed by losing one electron. When ground state molecule absorbs light energy, get activated. After activation, this activated molecule loses electron and that becomes a stable. This is stable as compared to this one. This is unstable and this is little bit stable as compared to this. So these are the 6 possibilities of stabilizing a excited partner. Now next one, molecular energies. What are the molecular energies are present in a given molecule? Okay. See. Right. Molecular energies are 4 types. There are 4 types of molecular energies are available. Molecular energies are 4 types. Okay, so this is translational energy. Second one, rotational energy. Third one, vibrational energy. Then electronic energy. These are the 4 types of molecular energies are there for any molecule. Translational, rotational, vibrational and electronic energy levels. Electronic energy levels. Molecular energies are 4 types: translational, rotational, vibrational and electronic energy level. Okay, so see. Right. The energy gained by a molecule for its free movement is translational energy. Translational energy is represented by ET, the energy gained by a molecule for free movement in space. Free movement in space, nothing but see, I am taking a diatomic molecule. This diatomic molecule is completely moving. So this is free movement. It is a complete free movement in space. Complete molecule is moving. So for that movement, how much energy is required? That is called translational energy, ET. So translation energy is non-quantized. It is not a quantized energy. We can't measure this one. Okay. So I can say it is a non-quantized energy. Not possible to measure. So the energy required for free movement of any molecule in space, that energy can't be measurable. We can ignore that energy. That energy is called translational energy. Next one. Same. The energy gained by a molecule for its bodily movement movement is moving bodily, which means if I take any atom, now this is moving bodily. This is called rotational axis. This is rotational axis, and this is rotation of atom or molecule. You can take any atom or molecule that is rotating bodily own. So take a molecule that will rotate like this. So suppose if you take this one, so freely it is moving freely. This is called translational. So if they rotate within the, suppose if you pass one axis from here, so if they rotate along that axis, that is called bodily rotation. So this is called rotational energy. Energy required for any atom for their bodily rotation is called rotational energy. Suppose if it is moving like this is called translational energy. This energy can't be quantized. We can't measure this energy. We can measure this energy. How much energy required for any molecule for their, what is this? Rotations. This is rotation. This is translation. Okay. So is it quantized or not? Yes. It is a quantized energy. It is quantized energy. Bodily rotation, it is represented by ER. Energy gained by a molecule for its bodily movement is ER. Moving with respect to body. It is quantized. But this is not quantized. Translational. Same. Energy gained by a molecule for its periodic displacement. Periodic displacement around nucleus is vibrational energy. It is vibrational energy. So this is represented by EV. Vibrational energy means vibrating from center of a nuclei. One is compression, other is elongation. Energy gained by a molecule for its periodic displacement around nucleus is vibrational energy. So here if I take A, so it is connected by B to spring. Suppose this is called compression, and what about this? This is called elongation. This is called vibration energy level. Take a spring, here nucleus will be there. This is a nuclei. This is at equilibrium. Suppose without movement I will be placed here. Without movement. Take a spring, a covalent bond. Now compress it, leave it. What happens? Elongate it, then compress. This is called vibration. So this is called compression, this is called elongation. So when any molecule absorbs vibrational energy level, they will undergo compression, elongation. This is called vibration energy levels. It is a covalent bond. This is a nuclei where 2 electrons are present. Nuclei between these two. Overlap. Covalent bond 2 electron. Now this is compression and this is elongation. So next is energy gained by a molecule for its unceased movement of electron. Unceased movement of electron is electronic energy level. So here you write one point, it is quantized. Remember, it is quantized. EV is quantized energy. This only translation is non-quantized, remaining all are quantized. Quantized nothing but we can measure. Non-quantized nothing but we can't measure. Energy not possible to measure. Vibration is measured. Now energy gained by a molecule for its unceased movement of electron. Suppose see, if I take A and B having a electron over here. Now this electron is moving towards right side, excited. It is excited. Now it is excited moving towards B side or moving towards S1 state. HOMO to LUMO. Electronic energy level. Okay. So this is ground state. Now after photochemically it will be excited from here to here. This is S0 state. Now this becomes a S1 state. This is called EE. This is represented by EE. It is also quantized. Suppose here if it is a negative pole, if it is a positive pole, always electron tend to move towards positive side only. Because electron carry which charge? Negative. Negative will always try to move towards positive side. That is called unceased movement of electron. Electron is moving from one state to other state. It will go to that side where attraction is very high. Attraction of electron is very high only when if they carry positive charge. This is called unceased movement of electron. Electronic energy level. What is electronic energy level? Lifting of electron from one state to other state. So what about E total? Generally E total depends on translational, rotational, vibrational, and what is one more? Electronic. So but actually see, total energy only three are quantized. We can ignore E translational because it is non-quantized. Total energy always depends on rotational, vibrational, electronic. Only these three. Total energy of any molecule depends on rotation, vibration, and electronic energy level. So if you take rotational energy level, this is R0, R1, R2. So this is 0 calorie, here 1 calorie, 2 calorie. So from here to here only 1 calorie of energy is required. This is called rotation energy level. This is for rotational. And if you take any vibrational, V0, V1, V2, this is energy. So here 0.5 kilocalorie per mole of energy is required for ground state. This is 0.5 and here it becomes 2.0 kilocalorie and here 3.5 kilocalorie. Energy between these two. So much? 1.5 from here to here, 1.5 kilocalorie between two vibration energy level. And if you take any electronic energy level, this is E1, E2, this is E3, electronic energy level. So this is almost all 1.0 kilocalorie per mole. Kilocalorie per mole, and here it is 3.0 kilocalorie, and here 5.0 kilocalorie. So from here to here 2 kilocalorie. 2 kilocalorie, and here 2 kilocalorie. Energy gap I am saying. Here energy gap is 1 calorie, here energy gap is 1.5, here energy gap is 2 kilocalorie. Only rough example I am giving, gap only I am explaining. Only gap. Don't compare one to other. Don't compare. You focus on 1 calorie, here 1.5 kilocalorie, here 2 kilocalorie. Energy gap. Minimum I am saying. It is not common. Minimum. Minimum for most of the molecule, this is the range. Maximum it may changes. Don't think like this. See, V0 to V1 1.5, V1 to V2 1.5, only that's it, enough. Don't compare sir V0 to V2 3.5, but E1 to E2 3.0, E1 to E3 5.0. Don't compare like that, because this energy becomes higher and this energy becomes lower. Don't compare vibrational and electronic energy level. I am explaining only gap, rough example for gap. Always rotation should taken in calorie, vibration and electronic energy level taken in kilocalorie. So finally, every electronic energy level, every electronic energy level having variable number of vibration energy levels. This is V0, V1, V2, V3, V4, V5, Vx, and here also remains same. And try to reduce gap every time. Don't write with same gaps. This is V0. Now V1, V2, V3, V4, V5, Vx. It is comes one more time in Jablonski diagram. Right now you remember, between two electronic energy levels, more number of vibration energy levels are present, V1 to Vx. And between two vibration energy levels, what you will expect? Rotation energy levels are present, R0. So this is R1, R2, Rx. Here also remains same. You write the small lines between these two, you will get R0. This is R0. So R1, R2 like that. This is R1, R2. R1, R2. So every time start with V0 in electronic energy level, and in vibration energy level start with R0. Okay, so every time in between these two you write R. Between 2V write R. These all are rotation energy levels. Every electronic energy level associated by vibration and rotational. Every vibration energy level associated by rotational. Which is the smallest energy? Rotational. This is electronic energy level. This you will understand one more time. Right now I am explaining rough example where vibrations are present, where rotations are present, where electronic energy levels are present, that I am explaining. E0, V0, R0. Here also E0, V0, R0. Here E2, V0, R0. Between two electronic energy levels, set of vibration energy levels are present. Between two vibration energy levels, set of rotation energy levels are present. If you know this one, Jablonski is easy for you. Jablonski diagram. Clear? So that is about molecular energies. Then see thermal and photochemical reactions. So where it will take place, right now explain thermal and photochemical. First one is importance of photochemical reaction. Second one is sources of photochemical reaction. What about third one? Activation, deactivation. Then fourth one is molecular energy. Fifth one is thermal and photochemical reaction. Clear? Now first thermal reactions. So how molecule is activated? Molecule is activated by heating. Molecule is activated by heating. Under thermally, molecule is activated by heating. So thermal reactions are, all thermal reactions are ground state reactions. All thermal reactions are ground state reactions. Means it will be S0 state only. Thermal reactions, molecule activated by heating, they are ground state reactions. Okay. So the chemical reactions, see the chemical reactions in which heat energy brings chemical change. Heat energy brings chemical change, they are thermal reactions. Okay. So when heat energy is absorbed by any molecule, that will brings change in their vibration energy level, and they will give product before reaching to electronic energy level. So I can say that all thermal reactions are ground state reactions. So when any molecule absorbs heat energy, they brings change in their vibration energy level only. Only this vibration changes, they never reaches to electronic energy level. This never reaches over here. They may reach up to here, vibrations. Whenever if it is reaches up to here, from there you will get product. Otherwise it will get down to ground state electronic energy level. But when any thermal reaction is taking place, that never reaches to E1. They reaches to Vx. E0 to Vx possible, E0 to V5 possible, E0 to V4 possible. But before reaching to E1, thermally molecule give change in their vibration energy level. Only vibration energy level changes, but not electronic energy level. Okay. So what you write finally this? During this process, change in vibrational energy level. Change in vibration energy level is observed. Observed in E0 level. It is observed only in E0 level only. Without changing electronic energy level, within ground state you will get thermal reactions. During this process, change in vibration energy level is observed. Okay? So within E0 level, there is no change in electronic energy level. So you can write like this. This is reaction path and this is delta G. Now see, this is called Morse curve. Morse curve. So here see, first I am taking lower energy, then I am increasing heat energy. When heat energy increases regularly, this will undergo this. See, here I am taking, this is E0, E0, V0 state, this one. Then this is V1, this is V2. So from here onwards, every time regularly try to decrease gap. When you decrease gap regularly, see, both will be clumps together. At one point it will start breaking. This is the point where it will breaks. The dot indicates final breakage. So what about this point? This is V3. Like this you can write at Vx. So first what happens, see, I am taking a molecule of AB. This is normal AB. I leave a molecule, this is AB. So this I am assuming as V0 state. V0 state. This state. E0, V0. Now I given heat energy. When heat energy is given, what happens? It may undergo expansion. Then this is the state of V1. Then I giving some more heat energy. If I give some more heat energy, what happens? Bond length is increasing or not? V2. Then somewhat heat energy. Then what happens? Is it heat energy increasing regularly or not? This is E1, B. Then A and this is B. Okay, this is V2. And what is this? V3. Okay. So now if I write a line like this, it looks like a Morse curve or not? So when you are keep on giving energy, then bond length between A and B are regularly increasing. Is it keep on continuously expand the bond length? Is it possible to expand continuously bond length? Or at one stage it will break down? E0, this is V1, A I am using. See, V1, V2, V3 is this one. V1, V2, V3. This is initial state without expansion. Take a rubber band, leave it first of all. Is it expands? No. But go for small stretch. Next stretch, third stretch, fourth, like continuously stretch. Is it keep on stretching? One particular stage where it will undergo breakage. That is called dissociation. That is called thermal dissociation energy. So here, what is the state of this one? E0. E0 V1, E0 V2, E0 V3, all are possible, but they never reaches to E1. Before reaching to E1, if any molecule undergo bond dissociation, that is called thermal reactions. Thermally it is undergo bond dissociation. At Vx energy level, see, this is V3, and what about this Vx? At Vx energy level, two bonded atoms having high stretch, due to high energy they undergo dissociation, bond breakage takes place, that energy is called bond dissociation energy. Clear? So before reaching E1, if any molecule participate in chemical reaction, that all are called thermal reactions. Okay? So, right. At Vx state, energy of reaction is very high. Involved in dissociation. involved in dissociation, nothing but breaking. So that is known as bond dissociation energy. This is called bond dissociation energy. So you need to remember Vx. Vx may be anyone. It may be V4, V5, V6, any. Depends on molecule. So don't think that Vx means minimum 3 possible. Vx is nothing but maybe anyone. Maybe V7, V18, V20, V40, anything. But continuous stretching one particular stage before reaching E1. Before reaching E1, so I not written V1. See, anywhere I not written E1. What is E1? E2. Electronic energy levels. What is E0? Ground state electronic energy level. Means all thermal reactions are ground state reactions. These all are thermally possible. This is thermally impossible. Electronic energy level never changes. Always whatever vibration changes, this vibration changes within E0 only. They never change in E0 even if changes, that is not thermal. Impossible. Thermally that is not possible. Thermally impossible to change electronic energy level. Electronic energy level never changes. Only vibration energy level changes under thermally. That's why they are ground state reactions. This they will ask in exam. It will comes one more time in Jablonski. Right now you know key points. What is vibrational, rotational, electronic energy levels, etc. So thermally dissociation possible? Yes, thermally dissociation possible. But that dissociation takes place within the electronic energy level, E0 state only. Then keep adding photochemical reaction. Molecule is activated by irradiating with light. Okay? Then what about this? It is excited state reaction. Excited state reaction, you can take S1, S2 like that. Excited states reaction. Excited states S1, S2, S3, S4 like that. Molecule is activated by irradiating with light. Photochemical reactions are excited states reactions S1, S2, etc. Chemical reactions in which light energy or photons. Light energy brings chemical change. During this process, change in electronic energy level is observed. Change in electronic energy level is observed. Here electronic energy level is observed here. So chemical change observed by irradiating with light. Here electronic energy level changes. Points are same, but this is ground state, this is excited state. So which is the most common state? The most common state for photochemical reactions is E1 state. So first electronic energy level state is most common because high lifetime, more stability as compared to other states. E1, E2, E3, how many are there? Many. Out of all excited state, E1 having more stability and more lifetime. So lifetime of E1 for electronic energy level, first electronic energy level I am saying. E1 photochemical reactions are very high, remember. E1 state reactions are different, E2 different, E3 like that. But maximum molecule will give products at E1 state only. Okay? How many electronic energy levels are possible for a molecule? Many. E1, E2, E3, E4, E5 like that. So all excited state reactions are called, all excited states reaction is called S1, S2 state. Right. The most common state for photochemical reactions for any molecule is E1 state. Why? Because E1 having high lifetime and stability. Okay, that's why E1 is preferred. Suppose if you want to write Morse curve, see, this is photochemically irradiated. See, here I am writing clear gaps, but actually see, you need to decrease the gaps here. Whenever if you keep moving over, gap should be decreases. This is E0, V0. This is V1, V2, etc. Now here also remain same. Here gaps are very less in number. Okay, what is this? E1, V0. Now V1, V2 like this. This is delta G and here reaction path. So what you observed here, see, it will be transfer from here to here. Possible. It is transfer from here to here. Possible. It will transfer from here to here, it is possible. Even it is possible to E2, E3, E4 like that. Such type of diagrams I can write many. What is this stage? E1. Suppose if I write one more same kind of structure over here, E2, same structure E3, E4, E4 like that. These all are called Morse curve. Okay, so this is Morse curve, this is ground state, this is excited state. Now, is it possible to show photochemically this reaction E0, V02? E1, V1 possible? Photochemically possible or not? Yes, photochemically possible. So E0, V02, photochemically I want to bring E1, V2, possible? Yes, E0, V02, photochemically. E2, V0, possible? Yes, it is possible. Definitely there is a change in electronic energy level. E0, E2, E0, E1, E0, E1. So maybe same vibration energy level, different vibration level, acceptable. But without change in electronic energy level, reaction not exist. See, here it is E0, then later on E1. You need to focus these numbers only. E0, E0, E1, E2, then followed by E1 comma, and this is E2 comma V0. Only these reactions are possible photochemical. Change in electronic energy level. So that is thermal and photochemical reactions key points. Then write the difference between thermal and photochemical reactions. What is the difference between thermal and photochemical? So write the key differences between thermal and photochemical. Difference between thermal and photochemical. Is it easy to carry out? Thermal reactions are very easy. Very easy to carry out. But what about here? Photochemical reactions are not easy. Thermal reactions are which state reactions? Ground state reactions. What about here? Excited state reactions. Photochemical reactions are excited state reactions. Okay? And see. Absorption of energy. Absorption of energy is non-specific. What it means? Only one atom never absorbs. One example I given. I written one circle, 4 dots I given, 200, 220 like that. So here all atoms in a molecule can absorb the energy. But what about here? See? Absorption is specific. Absorption of energy is specific. Absorption of energy is specific. Now, reaction intermediates are carbocation, on carbanion. Now here reaction intermediate is radical. Reaction intermediate is free radical. So in photochemical reactions, radicals are intermediate. There is no formation of cation and anion. Reaction intermediates are carbocation and carbanion under thermal. But under photochemical, these 2 points are important for exam. Absorption of energy is non-specific. Only one atom cannot absorb. When you give heat energy, only one atom cannot absorb. All atoms are absorbing the energy. When you give energy, only one atom is going to absorb. Only this is the key point. And one more, intermediate is cation anion, intermediate is radical. Okay, next. These reactions are favorable under polar solvent. Polar solvents are highly preferred under this case. Any polar solvent having polarity and dielectric constant. Alcohol, water, these all are polar solvents. Okay, but what about here? Favorable under non-polar solvents. Non-polar solvents are highly preferred. Benzene, CCl4, etc. Carbon tetrachloride, benzene, naphthalene, anthracene, all are non-polar solvents. Photochemical reactions carry out under non-polar. Thermal reactions carry out under polar. Water, alcohol, etc. Many polar solvents are there. Many non-polar solvents are there. This is last one. Strain molecules are not isolated. We can't prepare strain molecules under thermally. But what about in this case? Strained molecules are prepared. Strain molecules are isolated or prepared. We can prepare strain molecules. Ring strain, angle strain consisting molecule can be prepared. Strained molecules are easily prepared. So these are differences between thermal and photochemical. Then write molecular orbitals. Total 6 differences, key differences. Non-specific, specific, cation, anion, and here free radical, polar, non-polar. There is no preparation of strain molecule, possible to prepare strain molecule. Key differences between thermal, photochemical. So next concept, molecular orbital. From there onwards you will see electronic transitions. Then what is Hund's rule of maximum multiplicity, Frank-Condon principle, what is allowed and forbidden transition. Like that, then later on Jablonski diagram is going to come. These are the fundamentals where it will help in UV as well as photochemistry. Okay, so we know that linear combination of atomic orbitals produce what they produce? Molecular orbitals. Number of atomic orbitals equal to which one? Number of molecular orbitals formed. So what about additive combination? Additive combination produce BMO, bonding molecular orbital. What about subtractive combination? Subtractive combination produce ABMO, antibonding molecular orbital. These points already given. Where are given? FMO, frontier molecular orbital, already these points are given. That's why I am writing directly, very fastly. Linear combination of atomic orbitals. When atomic orbitals are combining, they are responsible to give molecular orbitals. Number of AOs will give number of MOs. Additive combination, if two similar sign overlap, BMO, opposite sign overlap, anti-bonding molecular orbital. This is called bonding molecular orbital. Suppose molecule having at least one lone pair exhibits non-bonding molecular orbital. If any molecule having lone pair, one non-bonding molecular orbital is available. If any molecule having at least one lone pair, we can also consider non-bonding molecular orbital. So always which energy is very high? Energy order. Energy of ABMO is greater than energy of NBMO, then energy of BMO. Energy of ABMO always greater than NBMO and BMO. Okay. So here sigma BMO otherwise you write sigma bonding. Sigma bonding and anti-bonding. Sigma bonding, anti-bonding overlap. See, I want to get sigma bonding. Can I overlap with same sign? Here 1 plus s orbital, here plus orbital is here. If these two are overlap together, what do you expect? If two same size overlap, what is this? This is called BMO or not? It is BMO. Suppose if two opposite charges are overlap, if plus minus overlap, what is this? ABMO. So this is called sigma, and what about this one? Sigma star. This is ABMO and this is BMO. So here this is called gerade and this is called ungerade orbital. Gerade and ungerade. So gerade means molecule having center of symmetry. Ungerade means molecule having no center of symmetry. Okay, if any molecule having center of symmetry by overlapping same sign, when two signs are overlapped together, that midpoint is called center of symmetry. That orbitals are called gerade orbitals. Gerade orbitals are that orbitals where they carry center of symmetry. Okay, inversion center or center of inversion, both are same. So between sigma BMO, sigma star ABMO, which is gerade? Which is gerade? Sigma is gerade. Sigma star is ungerade. This is called ungerade. Ungerade means no center of symmetry. This is called gerade. Gerade is represented by G, sigma. If anybody asks what is gerade means, any molecular orbital overlap responsible to give center of symmetry. That overlap is called gerade overlap. If overlap is not giving center of symmetry, ungerade overlap. U, represented by U. C. Now is it sigma or not? Here two p orbitals are overlapping. This is sigma, this is sigma star. This is gerade. It is a gerade interaction where two positive charges, two negative charges overlapping at one point. Over here they are overlapping. So but there is no overlap here, so I can say ungerade. Now no center of symmetry and here center of symmetry is present. Two p orbital overlap, two s orbital overlap is gerade, ungerade, gerade, ungerade. Clear? Second one, pi bonding and anti-bonding. Pi bonding and anti-bonding. Molecular orbitals of pi. So outright pi overlaps. Is it sideways overlap or head-on overlap? Pi. Sideways overlap. So two possible sideways overlaps are present. Now plus plus overlap, minus minus overlap. Plus minus, here minus plus. See, in this one, plus plus will join together and minus minus also join together. Now this is called gerade. Is it pi bonding or anti-bonding? It is BMO. And what is this? ABMO or not? Actually this is low energy and this is high energy. I am not writing energy order. Which is more energy? ABMO. Actually this you should write low, this you should write high if you want to write energy order. Suppose if you want to get clear information, you should write like this: energy. Energy decreasing or energy increasing? Energy increasing. From year to year energy increasing. Don't think that this symbol is indicate decreasing. Energy increasing from BMO to ABMO always. You can write like this, nothing will happen. But you should know the idea. Now see, plus plus, minus minus joining at one common point. This is pi bonding. Pi bonding. So pi bonding is gerade or ungerade? Sorry. It is ABMO. And what is this? This is BMO. BMO same sign overlap. Same sign overlap BMO. So now bonding, and what is this? Anti-bonding. So whenever if it is anti-bonding, what is this? Gerade. We can say gerade. So there is a presence of center of inversion. What about here? This is ungerade. Ungerade represented by U. So here no Ci. We can't write Ci here. Center of symmetry absent. So that is about molecular orbital. What type of orbitals are present? Only two orbitals are present for any molecule. One is Csir-Net orbitals, other is unChir. So whichever having same symmetry, electronic transition not possible. If any molecular orbital having same symmetry, electronic transition not possible. See, sigma sigma star possible, Csir-Net unChir possible. Pi to pi star electronic transition possible, unChir possible. Whichever molecular orbital having same symmetry, electronic transition not possible. Sigma to pi, Csir-Net unChir. Okay, then one more is sigma to pi star. Sigma to pi star, Csir-Net possible? No. So whichever molecular orbitals having same symmetry, Csir-Net, unChir, electronic transitions are forbidden due to symmetry criteria. Okay, so like this. So this is about molecular orbital interactions with corresponding atoms responsible to give molecule with Csir and unChir. In your next class you will see what is electronic transition. Electronic transition, what is multiplicity, what is allowed and forbidden, what is Frank-Condon principle, allowed and forbidden. After that, Hund's rule of maximum multiplicity. So later on we will see what is Jablonski diagram. Okay, so we'll stop here, we'll continue in your next class. So molecular orbital approach is over. Overall 7 topics are covered, starting from importance of photochemical reactions, then sources of photochemical reactions, then activation and deactivation. After that, molecular orbitals, energy or molecular energy, translational, rotational, vibrational and electronic energy level. Then thermal and photochemical, then differences between thermal and photochemical, finally molecular orbitals. So major concept is going to be covered from here onwards. There you will see what are electronic transitions, between which molecular orbital to which molecular orbital electronic transitions are possible. How many electronic transitions are possible for a given molecule. Then later on what is multiplicity. After that we will see what is Hund's rule of maximum multiplicity, allowed and forbidden. Then what is Frank-Condon principle. Okay, that is your upcoming class, that we will discuss in your next class. So tomorrow morning, today evening there is no class. Tomorrow morning same time 10:30 to 1. 10:30, not 10 o'clock, 10:30 to 1 you have a morning class. We'll stop here.